Welcome to the Nanovation Podcast. Information about this and other episodes can be found at fillerlab.com/nanovation. If you like what you hear, be sure to tell a friend or leave a review at Apple Podcasts. It really does help. I welcome your thoughts and suggestions. You can contact me on Twitter at Michael Filler or via email at nanovationpodcast@gmail.com.
My experience has been that the program managers in many of the different DoD areas have been very encouraging for you to come and talk with them, to talk about, what are the sort of core questions they're interested in, what are their real, problems that they're trying to address. And going and being a good listener, not just a good talker, sometimes is hard for faculty, but, going and really asking them and then stopping and listening.
That's Kira Barton from the University of Michigan, talking about one of the many things she does to help fund her research program. On this episode of the Nanovation Podcast, we take a deep dive into what it's like to be a professor. Suffice it to say, the job of professor at a Tier 1 research institution like Michigan is so much more than teaching undergraduate students. But before we get to that, Kira and I start by talking about additive manufacturing, how it's changing the way we make stuff, and her lab's exciting research on a new technique called e-jet printing. Whether you're here to learn about the emerging world of additive manufacturing or what it takes to succeed as a professor at a top engineering school, rest assured you'll be learning from the best. This is the Nanovation Podcast, an exploration of big innovations emerging from small things. I'm Mike Filler, your host and a professor at the Georgia Institute of Technology. Enjoy the show. It is my pleasure to have Professor Kira Barton on the podcast today. She is an associate professor of mechanical engineering and the Miller Faculty Scholar at the University of Michigan in Ann Arbor. Welcome.
Thank you. I'm happy to be here.
It's great to have you. You are an expert in control theory applied to lots of different applications. Why don't you give people a sense for your broad research program?
Sure, yeah. So just a little bit of background. Controls is often not clearly understood. It's essentially the background, that sort of the brains that are forcing all of your systems to try to behave in a certain way. And so what we do is we work on the development of the mathematics behind that and sort of the way of thinking about taking information from a variety of different sources and using that information to make decisions about how we want a system to behave. And when I say a system, that means anything from a 3D printer to a really cool robotic system to a car. So we work across a wide range of topics in manufacturing through robotics.
I was made aware of your research because you do some work in, I guess it's related mostly to the 3D printing space in micro and nano 3D printing.
That's correct, yes. The particular 3D printing process that we work on is actually one that's not commercially available. We're working to try to actually remedy that. But right now it's a process that's primarily in the research areas. It's a jet-based process in a way similar to inkjet printing, but using some different ways of getting material out. And it can actually reach feature sizes down to about 50 nanometers.
Okay, so that we need to come back to. But let's first take one step back, and why don't you talk and just kind of explain what 3D printing and additive manufacturing are?
Typical manufacturing is the opposite. It's what's known as a subtractive process. And so let me start with that one because it's a little bit clearer if you start there. Subtractive manufacturing means you start with a big bulk material, like a big piece of metal, and then you start to make shapes and designs and features out of it by taking material away. So you're milling or doing other processes to take that material away and then start to shape something. Now, what additive does, or 3D printing, what they do is a sort of inverse of that. So we start with very base materials. So these could be powders, these could be liquid form, and we build up layer by layer the product or features that we're trying to create. So if you want to make some type of say a metal brace, you can either take material away out of a bulk material, and then you're wasting a whole bunch of material by cutting out all these sections you don't need, or you can simply lay down the material in the exact shape that you want it to be in, layer by layer, and build it up.
It's funny. I think a lot of people who aren't working in the field get confused because they think, wait a minute, I build a house not by starting with a gigantic house and cutting it out. I add 2x4s together in an additive way. The thing is, we just have never really done additive at the length scales that you're talking about.
That's correct. Yeah, it is not in the concept of it like that. It's really not a new area. But you are correct in that the way that people are thinking about it right now is a little bit different, and that we're starting at these much more base, material sizes that are able to then create variations in your products on a completely different length scale, like we said, down to the nano features.
Right. So I had another question for you as a mechanical engineer. I'm just, I'm a lowly chemical engineer, so I don't quite understand these things. You talked about subtractive, and I was talking with a colleague the other day trying to understand where a technique like molding or extruding would fit in the pantheon of subtractive and additive. Because, extruding, you're pushing something through an orifice and you're making something in that process. And molding, you're kind of filling a mold, but it's maybe you made the mold subtractively, but each time you make the new part, you just kind of fill the mold and then you snap it out. How would you describe those relative to subtractive and additive?
Yeah, that's a great question. So I would say extrusion is actually a form of additive. There are definitely extrusion-based additive processes. So I think that clearly falls in that domain. I think molding, like injection molding, that one becomes a bit of its own entity almost, because I think that you are correct in that the molds that you make are typically the base component structure that you're going to fill. Those are usually made with subtractive processes, and then you have sort of this bulk way of putting the materials in there, and then the shape of the features within that are defined by this subtractive. So, that one really becomes kind of this dual process. It sort of requires bits and pieces of both. There are some really significant differences in molding that I would say differentiate it from what we would classically define as 3D printing. And that's because one of the key characteristics of 3D printing is flexibility. So the ability to customize what you're doing as you're going along. Yeah. And that's very different from molding.
Okay, so now that you're talking about one of the benefits, why don't you expand on that and maybe talk more about why building materials in a bottom-up or additive way is beneficial relative to subtractive. You talked about, I guess, the idea that you don't waste material, but there's all these other benefits in terms of part simplification and things like that.
There's many different things. Several of the attributes that people would, associate with. So there is usually less material waste, but in addition to that, that flexibility, that customization, what that allows you to do is to actually create features and internal features in particular that you just simply couldn't do using subtractive. So one way that comes in as an advantage is that you can take a component, say from an engine, and it might be made up of 30 different individual pieces that become assembled together. And you could actually think about designing it as one unique piece from a 3D printed standpoint. And so then another big advantage is that if you're building something up layer by layer, you can introduce some really cool material properties. So you can start combining different kinds of materials within the same layer. You can combine materials that have unique functional capabilities. So imagine you put down a conductive material directly in line with then a non-conductive, and so now you have an electrical connection. And so you're sort of embedding some functional capabilities into these materials directly as you're going.
That's fascinating. I saw a guy from HP Labs give a talk just the other day, and he was talking about something similar with hard materials and then liquids. So they were building these parts that had layers of hard material, and in the interstitial space, the printer was putting in liquid that then allowed the part to move in interesting ways. And it was all done at one time. And they were really pushing kind of 4D, the idea that it's not just the part, but it's how it evolves and moves with time.
Right.
But I had not yet grappled with the idea that you could think about different phases of material being printed together.
Yeah, no, it's very exciting. I think the design space that opens up when you think about 3D printing is really fascinating. And I think that is what's going to be one of the unique characteristics of 3D printing, is that you start to have to think about design from a totally different perspective.
So can you talk a little bit about how you'd think differently?
Some of it is just the features that you can create. So if I want to have a more efficient way of passing air through a valve, could I design a way for that air to circulate in such a manner that it dissipates heat? And so now I don't have to add on, say, a heat sink. So I'm just talking about like a metal part in an engine. Then I wouldn't have to maybe add another feature on top of that to do something. But because of the way that I designed the first part that was 3D printed, I'm getting an extra benefit. And so you start to think of these parts as not sort of single use, but more that concept of the individual who's talking about the 4D, but more of after you have this component built, what is the functionality of it? And does that now create some new characteristics that you just simply didn't have? And so instead of, just having an airplane wing, now I could build an airplane wing and embed throughout it all these different sensors that are collecting measurements on pressure and temperature and giving me this whole different range of understanding of what's happening with the flexing and all of that.
Yeah. No, I think you're exactly right. I mean, I don't see how this doesn't change how we have to think about building most everything. So you touched on briefly, and I have looked at your website, and there's a cool video I recommend people go watch on additive manufacturing that looks like you had a student put together.
Yep.
Very much worth your time, so go check it out. I'll put a link in the show notes. One of the techniques, and I think it's one of the ones you focus on, is this idea of electrohydrodynamic printing. And there's lots of different ways to do 3D printing. This is just one of them. So why don't you talk about what it is, why it's good, and what you all are doing with it? Yeah,
so electrohydrodynamic printing is a long word, so I'm going to call it EJet printing. So it's a little bit shorter.
Sounds good.
So the way that this process works is it's similar if you think about an inkjet printer. So it's the materials we start with are liquids, but that means that we could have particles suspended in them. They could be a vast variety of materials, but they are in liquid form. And then what we do is we create an electric field. And so similar to a magnetic field, it pulls the material. And so the electric field pulls the material out of a nozzle. So that could be any kind of glass or ceramic nozzle that has a sharp tip. And these can be down to nanometer, 100 nanometer size openings, but it will pull the material out and into this cone shape and then eject and deposit material from a cone. And the reason that that's important is that if I tried to push material out of these nozzles, I simply couldn't do it because it would require too much pressure and I would end up breaking the nozzle. And so that electric field actually serves as a way to break down the friction that's causing the material to want to stay inside the nozzle and pull it out. And then I can eject it into these very, very fine scale resolutions. So like I said, down to features that are 50 nanometers in size, which is very, very small, much smaller than any other 3D printing process. And then on top of that, what's really cool is that we can do that across a really broad range of materials. So these can be conductive materials. These can be biological. So we've done things with proteins or a DNA strand. These can be materials that are very, very thick, which would also be quite unusual. So they vary in terms of viscosity. So some are more like water, some are more like toothpaste, and that allows us to have a really wide variety of applications that we could use this process for. And so what we do in the lab is we do a number of things. We work to make the process more consistent so that we're seeing the same kinds of behaviors. And we do that by modeling, which means we want to understand what's driving the process. And then we combine that with ways of measuring what's happening while we're doing things, either while it's printing or after the fact. And then we put that into a control framework where we then take this knowledge about how the process behaves. We take this information that we measured and we try to come up with a decision about how should we change things so that it stays consistent, so that then we can push this process to be faster, have better yield, and just be a more viable technique.
Okay, so in a minute, I want you to explain a specific example where you've been able to do that for eJet. But before that, I had a couple questions about the technique. So I think you really beautifully explained this idea of pulling, and that that electric field allows you to do that. Being completely naive here, I would be thinking that I have a bunch of materials that I want to print, and they're going to be of opposite charge than the electrode that's doing the pulling. That they themselves will be repulsive to each other. And so I'm wondering, what is is that true? I don't know. And then what does that mean, or what is the limiting resolution of a technique like this from a fundamental perspective?
Okay, so for the first question about the materials, so some of these materials, they do carry a charge. And so what you have to kind of do with that is sometimes you can, again, with an electric field, you can change polarity. And so I actually have control in terms of being able to have a positive electric field, then a negative one and a positive, and I can alter that so that as I'm putting material down, rather than having them want to disperse away from each other, they're actually sort of attracted to each other. So that's one way. Yeah, that's one way we'll try to deal with that. You can do. Yeah, I mean that would be the biggest way for doing that. The second was the sort of fundamental resolution, and I think that's a very interesting question. I personally don't think that we have necessarily identified what that is. What we do see is that depending on material properties, and that includes both the material we're printing with, but also sometimes the materials we're printing onto. We see that the materials can cause the process to get into different kinds of what we would term regimes. And what that means is that we see fundamentally different behavior. So for some of them that are, I'll say they're nicely designed materials, they have a good property for this process, then we can continue to push that resolution. I think maybe down to something, certainly below 50 nanometers. I don't know if the process can get down to sub 10.
I see.
I think that's still really an open question. Okay. And I know there's a large number of researchers who are actively pursuing that.
So I just ask, from personal interest as someone who does additive manufacturing from the growth of crystals in an additive way, so we grow filamentary crystals, and we're able to modulate the gas phase composition as they're growing, and we call it encoding, right? So we can build these little 10 or 20 nanometer segments along the length of a crystal with differing compositions. And I'm always just trying to figure out where there are opportunities for one versus the other, or where they can be synergistic. And so that's really, really useful to kind of understand what people are thinking and what they're trying to to work on?
Yeah. I think that's a major open question is what is the fundamental limit? And is it, sort of is it material driven? Is it process driven? Is it simply equipment driven? I think that's something that people haven't answered yet.
Right. How about speed? Can you give us a sense for how quickly you can make these 50 nanometer features?
Yeah, so the process actually ejects relatively quickly. There's kind of two ways we can think about that. Obviously, if you're building something small to get to, from a nanometer resolution up to even millimeter feature sizes, or I guess overall devices to, even macro scale, that can take a bit of time. What I will say is that the material can release very quickly, so it can release 25 to 50,000 droplets in a second.
Okay.
And so yeah. So if you're moving, so if you have the ability to manage that volume of material, I will admit it's not a huge volume, but still, if you're wanting to create small feature sizes, you have to have a positioning system. So that means whatever is moving your print head has to be able to handle that kind of speed at a very high resolution. And that is honestly one of the limiting sometimes factors in being able to do that.
I was going to ask a kind of a high level question, a little bit related to how this gets deployed. I know that's much further in the future, but you mentioned inkjet printing, and I think people throw inkjet printers out the windows of their homes. I'm not saying I've done that, but I've come close. And so I just, one of the benefits, and this is, I think people miss this when they talk about maybe limitations of additive manufacturing, is that, at scale, when we have a lot of these scattered around, there are lots of efficiencies that come from the distributed nature of lots of 3D printers that are different than producing lots and lots of parts at one factory. And you just have to recognize that lots more benefit, not more, but different benefits come from that distribution. And so I'm just wondering whether you think ultimately this is going to be the kind of thing that's in our home, or is it going to be like Kinko's? Because we want to throw the inkjet printer out the window. I'll let Kinko's deal with the complexity of the printer, and I'll just shoot out a design and they'll do it for me and I'll go pick it up.
Right. So we're talking about 3D printing in general. I think you'll see both. I think for the hobbyists, you're going to continue to see better versions of the MakerBot type, 3D printer, which is, a fun thing that you can have in your home and play with. I think the kinds of process that I'm talking about that we work with in my lab, that's going to be higher end electronics. And so I think similar to the fact that you probably aren't going to sit in your garage and make your computer screen or make your the touch screen to your phone, you're gonna buy these. And so the folks who make high-end electronics, who make high-end optics, they're going to be the ones who are going to purchase these kinds of capabilities and put them into their facilities. And so then you as a consumer will simply be the ones that drive, what kind of capabilities do you want?
Right. So, okay, so now that you bring up high-end electronics, I'm curious if you could talk a little bit about, where you think that's going to fit into the manufacturing of these. Are you talking about displays? Are you talking about circuitry? Are you talking about all the above? I mean, where do you think it's going to most easily fit in?
I think it's going to be a little bit of both. I think there are certainly people who are looking at the optics side of things. I would say for us right at the moment, we tend to be a little bit more on the circuitry, electronic side, some simple sensors. But I don't think, we're excluded from being able to do some of the other components. I think what will probably initially start off, and this is the nature of 3D printing, is it'll have to start in high-end components because I think you mentioned this, the volume to sort of price ratio is not mass production, right? So it's not intended for millions of parts every year, at least not in the way that it's set up at the moment. And so if you start to think about a little bit more higher end, so, you want the next generation of something, but you sort of start with the higher capability. So if you think about even just where we get a lot of our electronics and our sensors and our technology actually comes in oftentimes from sort of military cases where they initially had ideas and concepts and pushed out capabilities, and then those technologies translated to the commercial sector.
Right.
So I think you might see some of that kinds of translations as well, where some of these things might go into automotive, they might go into aerospace requirements, they might go into, military operations. And then as the technologies mature and the cost is able to go down, then you start to see things commercialize towards the main group, I would imagine.
Yeah. So one of the things in that video you have on your website is these cool imagery of functional tattoos.
Yeah.
And talking about printing those. And one of the questions I had was, where do the active components go in that case? And kind of, are we able to? I mean, I'm pretty sure we're not today able to print electronics that are high performance and able to do, let's say, something close to silicon, low power, wireless communication, things like that. And so what we end up doing in these situations today is we have sensors that we may be able to print, and then we slap on an IC in a traditional silicon IC next to them. And I guess I'm curious, are you guys working on ways to build the electronics, the active transistors and such themselves with 3D printing?
I do think that's where people are going, yes. Yep. I think that's exactly one of the, some of those drivers, like the one on my webpage that's looking at these, tattoos that go directly onto the human skin and then can, take readings and wirelessly send information. There's a big demand for that kind of capability. And so definitely researchers are working on, and it's really not, it's not so much actually the question from the 3D printing side. It actually becomes a materials question of whether or not you can put together the right material combinations that can give you, as you said, that sort of functional capability that you want from, say, your standard IC.
Right. Yeah. No, I think it's a huge question, and it's an exciting question to see whether that's possible. One last question I wanted to ask you about before we move on is modularity. Right. So one of the things that you do with additive printing is you're integrating more things together, and it would seem that we have to be careful how much integration we do, because if you make a mistake on something that is a highly integrated product, it doesn't work. So you need to figure out where modularity can be introduced effectively, where you can sort, bad parts in a way that is cost effective. And I'm just kind of curious whether people are thinking about that, because a lot of what I see, again, as the novice in this area, is I'm taking kind of very simple building blocks and trying to build up everything versus having more modular components that I may try and print as I go, and just trying to figure out where I draw lines and different length scales, etc.
Yeah, I think this is a very important question, and people are thinking about this. And I can say from experience on our side, we are currently working with some folks in industry on trying to start to embed some sensing into some real components. And that's one of our big questions is, if you embed this sensing capability into, what would be normally a structure and wouldn't have this embedded in it, what happens if that sensing stops working? So how do you deal with that? But I think, some of the things that I guess that we've at least been trying to figure out is exactly that. So how do you start to think about the modular side, and how do you start to think about where would you fit in sort of redundancies?
Yeah.
So that you don't, with the first sign of something going wrong, you don't have everything sort of blow apart. It's kind of that whole idea with the Christmas tree lights, right? You don't want one light to turn your entire light sequence out,
Yes, sure. That's a
right?
great
So
analogy. Yeah.
yeah, we have the same concept. We don't want one bad trace to mean that the whole system shuts down. So starting to think about in terms of even electronics, how do you design the electronics for 3D printing so that you start to build in this reliability, so that you have a potential of changing, in a sense, something out or reprinting a patch on top or doing something like this so that you could continue to use whatever the product is.
Well, I'm convinced from this conversation and things I've seen in the last several months that this is huge. Maybe one of the biggest changes in engineering in the last 100 years. I mean, it's a big deal, and I'm excited to see where it goes. So,
oh, me too.
Yeah, well, I hope so. So one of the things that Kira graciously agreed to do is talk about, let's say, the logistics of academic life, what it means to be a professor, how you manage your time, what you're required to do, what's easy, what's hard, etc. I think the average person has very little understanding of what happens on a college campus. Most undergraduates go to classes and, they see instructors, but at a place like Georgia Tech or Michigan, that is such a small fraction of what faculty do.
That's right.
Yeah. So one of the ground rules that I'm going to lay out is that we're going to stay away from work-life balance questions unless Kira vetoes me. But I think the bottom line is that life as a professor is hectic and that life-work balance is always difficult. And all of us are always trying to find that balance, but I'm not going to ask any questions about that. So let's go ahead and I'll start with just kind of asking you how you got to where you are today. What path did you take?
Sure. So my path, it was fairly standard in that I went to undergrad, and I did my undergrad in mechanical engineering. And then I guess where I took a bit of a detour was right after undergrad, I had a sense that I probably wanted to go on to grad school and continue, but I wanted to understand what it meant to be an engineer out working. And so I took 3 years and I worked at two different places. I worked at a big, large engineering company where, I was one of thousands of employees and, had a bit more structure in terms of I was supposed to do this and then do this and then do this. And I did that for about a year and a half and realized that probably wasn't going to be the right fit for me. And then I went to a completely opposite spectrum. I went to a small research-based institution it was not a university, but it was a research institution where I got to work on a small team, really go through the whole process from designing something to building something to using and analyzing information. And I got to work with my immediate bosses who are all PhDs in their individual engineering disciplines. And so what this kind of did for me is it sort of opened up to my eyes some of the ideas about what you could do as a PhD in engineering. And I got excited about that idea and sort of realized that I needed to go back and get a little bit more education. So I then went to grad school, and through that process of grad school, I looked at lots of different types of ways of using my degree. And just when I went around and looked at the universities and saw the different pathways, the academic pathway really felt like the right fit for me. And so I happily accepted and took a position with Michigan after I did a 1-year postdoc with for my work and have been here at Michigan and happy ever since.
Okay, so how tough was it for you to go back to grad school after working for 3 years?
It took some time. It was hard. I will say that. You get used to kind of the non-student life.
Yeah.
You're making a little bit more money than you do as a student, and you have more freedom. So you have to kind of readjust back to that. But what I would say that I really benefited from is that I was more focused in terms of I had already had some experiences and I was more driven by what I knew I wanted.
Right. No, that I think having experience certainly does that. I went straight through, and I did co-ops and internships, so I had similar experiences out in industry at Intel and IBM, and those were transformational. I really happy I had those. At the same time, I'm happy I went straight through, because I think I would have had a hard time trying to turn around.
Yes, it is very hard for people to come back. So I don't necessarily always, advise people to go out, but I think in my case, it was the right decision for me.
Right. Okay, so I want next for you to explain your average day, and I'll just say that no academics day of the week is the same. So it's gonna give us a flavor. I'll also say that Georgia Tech and Michigan are certain types of institutions. They're similar types, but not all institutions operate this way. I would say we are largely research institutions, and so that will dictate what your and my average day look like. So for those listening, keep that in mind. This may not be what you want to do, but just why don't you give us a sense for what a day looks like?
Sure. Yeah. As you said, research is very big at both of our institutions. So that really is a major focus. I would say on a typical day, if I'm teaching, then I would have probably 2 hours blocked aside for the teaching component. But outside of those 2 hours, the rest of the day is primarily taken up with different combinations of meetings. And the reason for that is sort of twofold. There's many other things besides teaching that you do. And so some of those meetings can be comprised of actually office hours, so that's still kind of connected to the teaching aspect. There's also service that you are required to do, and that service is service in your department, it's service in the college, it could be service that's professional, so that might be that I'm an associate editor for a journal, and so, a meeting might be that I'm sitting down with the editors and we're sort of discussing things, or it could be my service associated with my department. So I have that, and the rest of the meetings that I would typically have are actually going to be research related. So those are meetings with my grad students, those are meetings with collaborators. Now, reason that a big part of mine are meetings is I actually run a very large group. That's a personal choice of my own. I like kind of the diversity of what we work on, and I like the large group, and I co-advise with many faculty, so we have collaborative projects.
So real quick, what is large? Can you tell us how many students, graduate students, and postdocs you have?
Yeah, absolutely. So I have about 13 PhD students. I have 2 postdocs. I have about 8 master's students and roughly 8 undergrads that work in the lab.
Wow. So is the master's program big at Michigan?
The master's program is big. It's about the same size, I guess, as the whole PhD program.
And these are students, do they pay their way for the master's program?
They do pay their way. That's the way that Michigan works. Occasionally, if they've been on a project working with me for a while, there are mechanisms that we'll have to go ahead and either provide hourly support, and in some, sort of unique cases, they might get a research assistantship, which would actually cover their tuition. But the standard is definitely the master's students paying their way.
Right, and so that's a big difference between, and maybe it's different in different departments at Michigan, but in Chemie at Georgia Tech, we have very few master's students.
Okay.
Yeah, it's not even something we do. There's been discussions about expanding this part of the program, but we really have very few master's students in the department.
Okay. Yeah, no, we have a very strong, large master's, and many of the students want research experience.
Sure.
And so they're actually willing to come into the lab. They'll take, they can take a research experience for credit. And so they take it as a course. They have to prepare presentations and reports, and they have to report out, and they get a grade for it. But they are willing to do that, and they want to take that as part of their curriculum.
I can see from a PI's perspective, principal investigator, i.e. you, that there is quite a bit of value in having people work on some things that maybe aren't externally funded yet and get things going. Is that how you often use these students? in the best possible use of the word use.
The master students you're talking
Yeah.
about? Yeah, I think master students they're very good for starting up maybe initial concept ideas,
right,
and getting that preliminary data, that preliminary sort of investigation that you then can use to help put into the proposals that you're going to write to show that you've got some pathway forward. Absolutely. And the other thing is that in my group, we do a lot of experimental work. And so we are both theory and application, which means that all of the PhD students have to also implement their controllers on a real physical system. And to keep those systems running, to bring on new systems. So if we're going to look into some type of control that requires multiple robots, and we're going to add a couple of additional robots, there's a lot of legwork needed to bring those robots online. And that's another great project for master students to help out with.
Right. That makes sense. So you talked about service teaching and research. So at a really high level, if you try and average your time across days and days, and what percentage of time do you spend doing each of those things?
The real answer, or the one that I'm supposed to?
Well, you're tenured, right? So what's the real answer?
That's true. This is true. Yeah. Well, okay. So the one thing to keep in mind is that summers, right? And this is where I think you also mentioned that lots of people don't understand, what faculty do. And summers are not, wow, we get them off, we get to go lay by the pool. Summers are like our core work period.
Right.
Because the grad students are all there. They're no longer in classes. We're no longer teaching. Actually, a lot of the service drops out. So the summers become very heavy researched.
Yes, right. So what percentage? I'm going to push you on a number.
So I would say that probably 30% of what I do is teaching. Maybe 10%, 15% is service, and the rest is research.
Okay. I mean, I would be similar. I think I'd be more like 20% teaching, maybe 10% to 15% service, and then the rest is research. So, not too far off.
We might have higher teaching loads.
You might, right. So we teach one a semester effectively.
Okay, we're supposed to teach 2 a semester.
Okay, there you go.
Yeah.
I guess it sounds like we're at a resort here.
Well, and that's not completely fair, because we can buy down. So what that really means is that we can offer to support the department through some research funds, because we were able to acquire them and then not essentially pay to not teach one of our classes.
Right. I mean, I think the main point here, and when you talk to undergraduates in your classes, what I find is they have no idea that they are the smallish percentage of your time, right? So they're thinking, if they look at it from their perspective, they're paying tuition, seems like a lot of money. They see us in class, and so they think, wow, this is what they do. They teach me. And then when I explain to them that this is not the bulk of our work, and that actually when you have instructors who are really good, you should thank them, because that's not what we're really incentivized to spend the most of our time on. And when people are good in the classroom, it means they really care about their students and teaching.
Right.
And some of them just their mind kind of explodes that that's the case. But it is, I think. Yeah, no, I agree. And I think that, as you said, I think a lot of it is the incentivizing, but also that the university itself, right, is that these are research institutions. And so the sort of reputations, what they're known for, it's the faculty, and that comes from the research the faculty are doing. And that does also then lead back to the students. But as you said, there's a lot more that has to go behind that. And it's not that you're spending 100% of your time preparing for these courses. It's that you've got all these other things you're juggling. Right. So you mentioned that you have a large-ish group. I'm not going to say it's large, because I've know several groups that are like 80, and that to me definitely meets the definition of large. Yours seems very reasonable to me, right? So can you talk a bit about, from your perspective, what is an optimum research group size and why?
Yeah, I think this is, as you said, from my perspective, because this is very faculty oriented. Certain faculty, their nature of their work might not dictate that they can have as many students, and they may just prefer not to. I think for me, I like around this size, sort of 10 to 13 PhD. So I sort of think in terms of the PhD students, because that's really the group that requires or has the most time with me and that I spend the most time with. So they're there for 5 years. You're really invested. You're finding the funding to support them. That's a big commitment. Now, what's nice with the postdocs is they can come in and sort of help, shape and keep things going and mentor and all of those pieces. And then the masters and the undergrads, they come in and they get to, as I said, they can start new research ideas. They can pick up and do some of the experimental work. So they're a big support mechanism. But for me, I like that sort of 10 to 15 is a good size. One of the reasons I like that size for my own personal group is that I feel that we do, as you mentioned, have a relatively what seems like large breadth in terms of the application spaces, but the core fundamentals of what we're doing are all at controls. And across that domain, then the students have lots of opportunities to talk to each other, to work together, to share ideas, to learn about another area. And so I see these group interactions and the sort of synergy among the students, and I really enjoy that aspect.
Yeah, and I think in terms of efficiency, if I get really dry for a second and say, what do? We spend taxpayer money. So how are we most effectively using taxpayer money? And we want to produce both research, but outstanding PhDs that are going to go on themselves and change the world, right?
Yep.
And
yep.
So having had those students be able to interact enough and experience these synergistic things is really important for their future success and their knowledge, et cetera. And so too small probably doesn't quite hit that. Too large, I really worry about the efficiency and the productivity per student relative to taxpayer investment dropping.
Right.
And while I think we all hope that our research goes to exciting places and helps change the world in whatever way possible, our main product is the students and the
Yep.
combinatorial nature of having many students, that they themselves go off and do something that you want all of them to be as outstanding as possible, and the taxpayer does too.
I agree. Yeah, I completely agree with that. And I do agree that too big and people may just get lost in the shuffle.
Yeah.
And then they maybe don't get the mentoring that they need, and then they don't necessarily go out and become strong, independent researchers, which is what you want. Absolutely. That is what we contribute. That's what we give is the students.
Yeah, I agree. So then, okay, so you have a core competency, but you work and apply that to different applications.
Yeah.
Can you talk about how you choose scientific problems to work on, right? Because that is a matter of liking it, needing to write proposals, needing to get them funded, right? How do you make decisions about which directions to go in?
I think that the way the decisions get made changes as you go along. I think when I started, I was very closely tied to things that I had probably worked on as a PhD student. And so most of those were independent. Most of those were my ideas that I started with, and they were really sort of single, principal investigator with a student type ideas. What I'm finding as I, have more years at the university is that I'm more drawn to sort of bigger problems that require a multidisciplinary, collaborative approach, which means that now you have a much bigger problem, and it potentially has the element of where it could have a much bigger impact, but it's going to require expertise from several disciplines and different faculty, and so you start to have to think about how do you build these groups and these teams and make them effective and productive. But I find that is driving a little bit more of some of the directions I'm going now, because I like working with other people, and I like that the diversity of kinds of problems and the sort of big aspect of some of the problems you can go after if you have a multidisciplinary team.
Yeah, I'm entirely the same way. I love my job 10x when I get to collaborate with people who do different things and tackle bigger problems. One of the questions I wanted to ask you is how you go about doing that from the perspective of funding. You know, one of my experiences has been the more interdisciplinary you get, you're in the middle ground, right? Between the definition of interdisciplinary, you're between two disciplines, and so talking to someone and trying to convince somebody who's in one of those disciplines to fund you, they may say, I don't really see why you're over here on this fence, and then you go on the other side of the fence, and that discipline kind of says the same thing. So how do you figure out how to convince somebody that this is worth doing?
Yep. Yeah. I think. So one of the things I've noticed is particularly with the National Science Foundation, they've actually started to put a bit more emphasis on multidisciplinary collaborative efforts. And so they're actually building some programs that are specifically designed for that. If you don't fit still into one of those, what I've sort of ended up working to do is to identify in this problem, in this first part we want to address, where really are the fundamental questions. And they may be motivated by a different discipline, and they may require insight from a different discipline. But if the fundamental question, if we can convince somebody that the fundamental question lies in this domain and pulls from these others, but the real, contribution comes from here, then that's the way that we try to pose that question.
Yeah, I think that's exactly right. Every time I've been successful at something interdisciplinary, it is anchoring it in a community that will recognize the fundamentals and convincing them, but it's applied to something you've never thought about before, and they tend to go for that kind of thing.
Yep.
So for people who aren't familiar, how do you go from an idea, maybe independent idea or something with collaborators, to funding? What does that look like? Let's say, I don't know if you have DoD funding. I'm not, let's put NSF aside. That's a little bit more straightforward. But DoD or DOE or something like that, from the idea to getting money, what does that look like? And what are the challenges?
So let's say take DoD. I think an important part that I've experienced with that is getting to know the program directors and managers. And so looking into what are the kind of key areas that they're interested in. And then my experience has been that the program managers in many of the different DoD areas have been very encouraging for you to come and talk with them, to talk about, what are the sort of core questions they're interested in, what are their real, problems that they're trying to address, and going and being a good listener, not just a good talker. Yeah. Sometimes is hard for faculty, but, going and really asking them and then stopping and listening and hearing about what the different problems are, and then trying to understand if some of the work that you do can fit into the context of addressing a part of that problem. And then, starting to build those relationships. So I found that to be very fruitful and also really necessary in order to make headway and have success in the DOE, the DoD, those types of funding groups. Another big piece, and we've talked a little bit about this, but is having that preliminary sort of data set or proof of concept that shows that not only have you thought about the problem, you started to think about and actually implement a few things in terms of tackling it. And that gives you credibility and being able to not just show that you have maybe background, but you're actually working on the problem and have some credible ideas moving forward.
Yeah, going back to the listening to program managers comment, I think people miss that they have a program that has goals, and they're looking for academics to help them fulfill those goals. There are some funding opportunities that are a bit more open than that, give people freedom to do whatever they want, but those are relatively few and far between. So you have to figure out how to solve their problems, fit your work in a meaningful way into
Yeah.
a context that works for that particular program manager.
That's right. That's right. And it is very important, like we said, to listen and understand and make that connection so that you're not just a faceless proposal, but you've been there, you've talked to them, you've met with them, you've sat down, you've listened, you've written what's called a white paper, which is that, initial idea. So I think those building that kind of relationship and also just, specific problem that you're working to address is important.
The fact that you run a 13-person PhD group is no small feat. I think it's really important for people to recognize that that's not easy to do. Requires a steady funding stream. Every student per year costs approximately $110K at a place like Michigan or Georgia Tech. So to run 13 PhD students, you're bringing in somewhere between $1 and $1.5 million a year. And so can you talk a bit about how you keep your portfolio steadily funded? Is it diversification? What are your techniques to, try and maintain funding to keep everyone employed, so to speak?
Right. Yeah, I think diversification is actually key because, the funding agencies, different funding ebbs and flows. And so you want to have several different pots that you can go to, and it's across a number of different ways. So there's industry, which is an avenue certainly to try to go after, particularly for some of my work. That's a good resource. Obviously, the National Science Foundation, the Department of Defense. If you can distribute the funding requests across these, then you get to tackle different kinds of problems and different sort of levels of those problems. And I think that becomes very important. If they all came from one source, I think it would be extremely hard to do that. Agreed.
Okay, I have one more question for you, and then we'll wrap up. So, what's your least favorite thing about the job?
My least favorite thing. Wow. That is hard. It's funny. I know my favorite thing, but my least favorite thing.
I have a least favorite thing, but if
what's your least favorite?
My least favorite thing is grading.
Okay. Yeah, I do agree. Grading is not, although I actually like making exams and such, grading is not as
Does that come
fun.
from like a diabolical perspective?
I wonder if that's maybe a little bit what it is, because I certainly as a student I hated exams, and now I'm like, oh, this is fun. Let's think of it, But as everyone says, if you think it's an interesting, fun question, nobody's going to like it.
Right.
Yeah.
So what's your favorite thing then?
Definitely my students. I mean, that's not a question. I really enjoy the interaction, the sort of watching them progress and come in as, many of them, like yourself, go straight through. So they come in, they're 22, they're sort of in undergrad mode, and to see them mature and progress. And by the time they finish, they've got their own ideas. They're confident in what they know and what they can do. And, they're just ready to go out there. And that's a very good feeling.
Kira Barton, thanks so much for taking a few minutes.
Thank you very much.
You've been listening to Nanovation. If you enjoyed the show, please leave a rating or write a review on Apple Podcasts. Show notes are available at fillerlab.com/nanovation. Nanovation is recorded in the Marcus Nanotechnology Building on the campus of Georgia Tech. Andrew Cannon edits the show. I'm Mike Filler. See you next time.